And we're starting the recording. Yeah, so welcome everybody to the first Computational Audiology Network seminar. This is a new series we're starting and we're organizing together here with Jennifer. Hi, Jennifer, maybe you want to say.
Hi.
And exactly, and Jan Willem Wasman. Hey, Jan Willem.
Hi, great to see. Well, trying to let everybody in. It's quite busy now.
Yeah, maybe we give it 1 minute more or 2 minutes more, as we know there will be more coming in the first couple of minutes. So if we go to the first slide again, please, Jennifer. Yeah, the first seminar is on deep learning for better hearing, the benefit and potential of deep neural networks to improve speech perception with hearing devices. And that's a really cool topic, really interesting, at least for me. I'm slightly biased, I guess. But the idea of these seminar series and sessions is now to highlight and focus on very interesting state-of-the-art topics in hearing science and audiological care. And we start off with this one, where we look at new machine learning and artificial intelligence methods for hearing devices. And then I hand over for Jan Willem to tell us a bit about the updates.
Yes, great. I was only allowed to talk for 1 minute for updates about the Computational Audiology Network. And I must admit it's quite stressful because there's too much to share. So I will not go over everything in this slide. I think much of the things you can find on our website. But I would like to mention that at the World Congress of Audiology in Seoul, we will organize our annual CAN Special Interest Group members meeting. So everybody who is already member will be invited. If you're not member yet, please go to our website to subscribe. The agenda will be shared soon. And of course, because it's for members and by the members, feel free to contact me about topics you'd like to discuss at this meeting. So I cannot go over all the points here, but I wanted to share also one secret, maybe the secret of success that people wonder, how can you do so many different activities? And I think what's really important is that we try to facilitate people with their own initiatives. And one great example is that maybe 2, 3 months ago, Jennifer reached out to us. She wanted to be active within our network. And we shared our working plan. And then she thought, well, I've already experience of organizing seminars in Brazil. And if you like, I can help you out here at this seminar. So obrigado, Jennifer, for taking this initiative, and great that now within a couple of, maybe 2 months, we are now hosting our first seminar, and hopefully we'll have more new activities in the next months to reveal in Seoul or at the VCCA in June. We can provide some more details in the chat, but I guess I'm already talking for way more than 1 minute. So thanks you also, Toby, for organizing this, and looking forward to our first CAN seminar.
So, hello everyone, welcome to our first seminar. So, this first seminar we will have two presentations. The first one with Professor Dr. Stefan, and the second one with Professor Dr. Tim. Each presentation will have 20 minutes and 5 minutes for questions. And in the final, we will have an open discussion. So, Toby, you can introduce our
Yeah, thank you, Jennifer. So it's our great pleasure to welcome our two speakers today. This is firstly Professor Stefan Launer from the Sonova company in Switzerland. Hi, Stefan.
Hello, thank you.
Great that you could make the time to come here and join us for the first CAN seminar. That's highly appreciated. We've just smashed through the 100 participants in this meeting mark, which is great, I think. So quite a few people in the audience today. And yeah, Stefan is a long-standing expert in hearing science and hearing research and product development. Has worked at Sonova for many years, I think, and led various teams in audiological engineering, digital signal processing, acoustic design, and so on. And now he is vice president, I think, of the Audiology and Health Innovation Program. He also holds a adjunct professorship in audiology at the University of Queensland in Brisbane. And then secondly, we have Professor Timo Gerkmann. Hi, Timo, welcome.
Hi, nice. Thanks for having me here.
Yeah, so Timo is really also a leading researcher in the academic field in acoustic signal processing and now also in deep learning and using AI for speech processing. He's a professor at the University of Hamburg and has held many different positions here. I've seen in your CV and at Technicolor Research at Oldenburg University, at the Royal Institute of Technology in Stockholm, in Bochum, or at the University in Bochum and Siemens Corporate Research in Princeton, USA. And he's really an expert in statistical signal processing, machine learning, as I said, and also a senior area editor at IEEE. So we are really happy to have you two here, and I think it's great to have two perspectives, one from the company industry side of research and development, and then from the academic and state-of-the-art research side, maybe from the university side. So let's start with Stefan's talk then. Maybe if you could try to share your slide, please, Stefan. We will have about 20 minutes, then we have some time for questions. So if you want to ask questions, please put them in the Q&A here or in the chat, or we can also let you ask them in person then if we have the time and you're happy to, if you raise your hand, basically. And then we have Timo's talk with a bit of time of questions as well. And then we have an open discussion afterwards with everybody together. And the idea is to make this a bit more interactive. So everybody who's happy to join in or ask questions or join the discussion, then please, again, put in the QA, put in the chat or raise your hand and we try to make that happen then. So then I hand over for Stefan's talk. Take it away.
Yes, good afternoon, good morning, good evening, wherever you are. Thank you, Tobias, for inviting me. Tobias, Jennifer, Jan Willem, I don't know who organized it, but thank you to the organizers for inviting me and presenting here. It's always a pleasure and it's always a little challenge. What are you presenting to such an esteemed group? So I want to talk a little bit about deep learning for hearing instruments and discuss some practical considerations. And basically, I will focus in my presentation on hearing aid functionality. So DNNs, deep neural networks, AI applications for speech enhancement. But I also wanted to briefly at least mention and raise the issue that with the modern AI tools, we can also improve the hearing care delivery a lot, and we can also apply it to product design. So how we design the products, the shells, the acoustic domes and things like that. And I think at some point that would be also very worthwhile topics to discuss in the future. But today I want to focus on DNNs to improve the hearing performance of our systems. And I think one of the key points where I see lots of potential for AI to improve the functionality, and I think that's what we are seeing today, is to help us improve speech intelligibility in complex listening environments. We had in the past, we had wonderful solutions with the directional microphones that already gave quite a bit of benefit. However, as Barbara Jean Cunningham once called them, they are a little bit acoustic blinders in that they focus on one direction and suppress a lot of other things. And especially in dynamic conditions, that is a disadvantage. And that's where I also see a huge potential for DNN-based solutions, more dynamic, better performance in more dynamic conditions. There is a wonderful paper also summarizing the challenges of getting deep neural networks into real hearing instruments. It was published in 24 by a Chinese group and together with Brian Moore, Chengji Zheng, published it and nicely summarized the challenges that we have. DNNs with especially a particular size and architecture are computationally complex. And that is difficult to achieve in the hearing instruments, especially given the size and power constraints we have. Also, they potentially introduce quite a bit of delay which is a potential challenge for the hearing instruments. In hearing instruments in real life applications, the delay should be less than 10 milliseconds, maximally 15 milliseconds, as I write here. So delay through large DNNs might be a huge issue. And next, if we develop DNNs and we want to put them into products, we have to make sure they really work in daily life environments and they don't screw up things. So we need a very, very solid and large training database so that the DNNs really work well and generalize well. And then finally, if you want to apply them in hearing instruments, the question is, how much do they suffer from real life applications where you have people with a mild hearing loss who tend to have more open hearing instruments, and in open fittings, people tend to lose the benefits that typical noise reduction schemes provide. So a very nice paper, nicely summarizing the trends over the past 60 years and the recent trends in AI research. One of the challenges that we have, as I already said, when bringing large-scale DNNs into hearing instruments is the power consumption. This graph shows the computational power of a chip as a function of the electric power consumption. And the target range for a hearing instrument sits down here. And typically, this is a range 1 to maximally 10 milliwatt power consumption, where basically very few commercial chips are available that would have the computational power to operate larger scale DNN. So one of the first practical hurdles to overcome is, how do we get a chip that fulfills this power constraints? And basically, we developed a chip ourselves, and from our perspective, you need a separate processing unit, a full-blown neural processing unit with a very specific architecture, a different architecture than a conventional DSP has, that is perfectly well suited to operate different types of DNNs. So you need kind of a DNN co-processor or specific chip to operate in a hearing instrument with a power consumption of less than 10 milliwatts, which is a challenge. And from our perspective, this chip should be capable of operating different types of DNN structures, so the classic convolutional neural networks, but also recurrent neural networks, which are important for the processing, especially of dynamic signals like the speech sounds. So that is one practical hurdle to overcome, have such a chip available, and then get the DNN on such a chip and integrate that chip into the hearing instrument. A second major point is to develop a DNN and then to train it to fit on such a chip. So as I will also explain in the next slide, we have chosen for the DNN in hearing instruments an architecture which is called a UNet architecture. I'll explain it in a second. A combination of CNNs and RNNs with multiple layers. And such a network needs to be trained. And when it needs to be trained, it needs to be trained for actually two aspects. One, it for sure needs to be trained to optimize, to provide optimal performance for intelligibility, and especially also for sound quality, where we had different metrics that we used to train this DNN, and they are published and the citations are given here. A second major point that needs to be trained is the entire architecture needs to be trained for the hardware that is underlying to compute the DNN. So basically, you need a training system and you need sounds and sound databases that include two aspects: a metric for the sound quality and how to assess the performance of the system, plus a metric to optimize it for the underlying hardware in order to make sure that the system optimally performs on the target hardware that you have in the system. So that's a second practical consideration that is very important to think about and to build when you want to get a solution into a hearing instrument. As I briefly mentioned before, the architecture that we have chosen for speech enhancement in hearing aids is this UNet architecture. Basically, it's a DNN structure where you have a combination of convolutive neural networks and also recurrent neural networks or similar components to reflect the spectral information and also the temporal information of speech sounds. The architecture that I'm showing here has evolved. It has roughly approximately 10 hidden layers and several skip connections. And the work, the underlying algorithm is also published, and the citation is here. Basically, this architecture of a network creates a complex ratio mask, amplitude, and phase that is then multiplied to the speech or to the input signal, and in this way extracts the target speech signal directly from the background noise. So it's a direct extraction of a target signal through a DNN. It's a pretty big network. It has several million parameters, and as I said, 10 or more different layers. What we noticed is that when you apply such a network architecture, the performance definitely increases with the network complexity, but there is also a certain point above which the network complexity, at least in the context that we were applying it, does not necessarily improve the performance with the measures that we have any further. So there is also a certain optimum here. But again, for us, what is important in order to drive these networks, they require a specific NPU chip. And what we learned over the course of time, over several iterations of implementing such systems on hardware, is that if you have a specific computer chip, you can drive a lot of optimization of the performance of the system when you know the physics of the underlying chipset. That allows a lot of parameter optimization that reduces the memory needs, and it allows to reduce the power consumption between iterations significantly. So when we had the first version of the chip to the second version of the chip, simply by knowing the target hardware and its physical properties, we could save more than 30% power consumption, and we could also significantly reduce the delay through the system. So that's a very practical learning that we have, how much it can be optimized when one has the physics of the chip under full control. So overall, to get a DNN in a hearing instrument, from my perspective, it needs a powerful DNN architecture, and I'll come to the benefits and the clinical studies in a second. But then it also needs a good training platform and measures that you can use in order to optimize the DNN and also to train it for your target architecture. And from my perspective, it needs a powerful and a really specific coprocessor to run in a hearing instrument context. The classical DSPs don't have the power to do that. So I want to briefly talk about the clinical results and show the benefits that solutions like that can have to patients. For us, it is very important to take a broader perspective also on the benefits, not only think about audibility and the classic speech intelligibility dimensions, but also look at other benefit dimensions that these systems might provide, like reducing listening effort and fatigue, improving attention and cognitive abilities, and also improving, for example, social integration. In one study that we did together with the Hörzentrum Oldenburg, we switched from a static to a dynamic condition. And as I said, that's where I see, or we see, a huge benefit of these DNNs, because they are not acoustic blinders and can react and extract the strongest target speech signal. So in this condition, we had speakers coming from different direction, and the target speaker was always identified with a call sign, but it could come from any of the three directions. And you can see here in a study with, I think it was 17 moderately hearing impaired people, that when using a DNN, as I described it before, you get 20% roughly speech intelligibility improvement over the classic binaural directional microphone system in the condition described above. And you see a slightly larger benefit in the retest. What you also see is that it's not only the intelligibility that is better in this condition, but also the overlap that you can allow between different talkers. So in a fast-paced conversation where people don't always let others finish the sentence, you have a certain overlap. And with a DNN, people are better to extract speech signal at a higher pace, so a larger overhead, and that even increases when the test takes longer. So you have two advantages here: significantly improved speech intelligibility in dynamic conditions, and also from kind of an attention measure, a larger overlap that is possible and can be allowed. We also measured listening effort, and here you see the results of listening effort scaling using the Ackerless scale in 3 different labs. We always had a very similar setup as we had it before, slightly different arrangements of target source locations and background source locations. But in all 3 studies, you basically see that when applying the DNN versus a binaural directional microphone, you can see a significant reduction in the effort that persons scale at the same signal-to-noise ratio. So a pretty strong effect that you can see here. And this effect can also be observed when you do physiological measures. And in this study that was recently presented by Anne and Dave Eddins at the AAS, we basically for the first time measured speech intelligibility, blood flow in the brain using FNIRS, and neurophysiological brain activity, so EEG data in the same subjects. And we can see a significant improvement of speech intelligibility in a complex condition, as I described it also before, while you see a significant blood flow reduction in the auditory cortex and in a linguistic center in the front of the brain, when comparing the DNN again with a strong binaural directional microphone. And at the same time, you see a stronger activity in the part of the brain where the speech signal is passed and extracted. So improved speech intelligibility, less energy, and through better speech passing in the brain. So pretty significant improvements that we can get here from using these powerful DNN tools. So overall, when we look at the performance that we can achieve with these DNNs, and I'll come back to this benefit pyramid that I showed earlier, we find benefit of these DNNs on multiple levels, on the basic speech intelligibility in complex environments, on effort. I'm also showing here the example of a memory test that we had, and we get, when we use surveys, we get far better results in terms of the judgment of people, how they feel about the system, and how they benefit from the system and the benefits that they described. And we also noticed that in positive observations of significant others when people use these technologies. So from my end, from a clinical perspective, these DNN-based speech enhancement algorithms really provide a lot of benefit for the patients, for the users of the devices. When we think about the hearing instruments, I also clearly see a lot of future applications, and I now focused on one specific solution for speech enhancement in the cocktail party condition. But there are other conditions where we could also benefit from DNNs. And I think here I list a broad range of topics. DNNs are not only good for speech enhancement, they could potentially also provide significant benefits when it comes to restoring audibility. There is a lot of work going on using DNN-based algorithms and auditory model-based algorithms in combinations with DNNs to steer the gain settings and the amplification schemes, or also to apply DNNs to reduce artifacts like wind noise or feedback. So lots of future applications, and I'm also looking forward to Timo's talk to hear more about his perspective. Now, to summarize, I think really DNN-based algorithms provide us with a huge potential to drive the performance of the hearing aids really forward. I think when thinking about the DNNs, we should also think broader about the benefit dimensions and in what situations are we using these DNNs and for which specific hearing use case do we apply them. So far, we have tested the DNNs mostly for mild, moderate hearing losses, but also for some profound hearing losses, and found the same or even better benefits also in CI patients. We have done most studies with adults, but recently also one study with children, and also there we found some interesting differences, but also significant benefits. So overall, again, huge potential for future improvements. And as I said also in the introduction, we should also think more about how to apply AI to improve the care delivery process and how to improve also mechanical design aspects of the products. And yeah, you said questions. I do have a lot of questions to the audience myself. So for me, the approach that we have taken is a large one-size-fits-all DNN. And I'm wondering, is this the best approach? Are there other DNN architectures that would be better, maybe much smaller, very application-specific DNNs for specific use cases? Also the topic of how do we apply DNNs to different functionalities beyond speech enhancement. And also there is quite a bit of a hype around these DNNs, and I think we should very carefully consider where do they make sense and where are the classic signal processing solutions in terms of power consumption, in terms of computational requirements, still a very good option. And finally, from my end, we have tested it with people with mild hearing losses, but not with normal or minimal hearing losses. And I wonder whether these powerful speech enhancement tools also help people with almost no audiometric hearing loss, but subjective listening difficulties. Anyways, these are questions I would also love to discuss and explore moving forward. So thank you again for organizing this. I think it's great, and thanks for inviting me.
Great. Thank you very much, Stefan. I think there's a lot of virtual, oh wow, yeah, there's really a lot of virtual applause here coming in.
Thank you.
This is great. We can't hear it. They should make a bit of a sound sample with it, but yeah.
That would be cool, actually.
Yeah. And I bet you know many of these names that are, yeah, they show the little names, which is nice. Great. Thank you very much for this great overview and talk. We have a few questions for you right here. I think we could go into that and then we continue later also in the open discussion with more. I also like that you put your own questions here, which is great.
Yeah.
So the first one is from Clara, where she asks whether the non-DNN solutions or comparisons, I guess, also included traditional signal processing noise reduction methods.
Well, I mean, when I showed the results, basically the results are always for um, very classic hearing instruments. So they include the full signal processing stack of hearing instruments, basically all components of gain models, the classic speech enhancement tools, and also whatever feedback management system it has. And then we switched between the DNN with a full-blown hearing instrument versus the DNN. We use typically two conditions: the standard omni microphone, or in this case, a real ear microphone, and a very strong directional microphone, either a monaural directional microphone or, in the results I showed today, a binaural noise reduction scheme. So it was kind of best-in-class solution we had before the DNNs versus the new DNN. So the classic noise reduction schemes were the comparison.
Yeah, great. Thanks. That answers it, I think. Then the second question came from Brian Moore, where he found that he's actually using such a hearing aid, I think, himself, and he found that with the DNN activated, other sounds and speech, such as environmental sounds and music, they all sound pretty okay, actually. They're not too bad, he says. Is this just luck, or is it actually a intended effect on how the DNN was trained on your side?
No, I think, this is really, really a huge issue in the training. And that's what I tried to say also earlier on. One of the big issues in practically designing algorithms for hearing instruments always is to make them robust so that they don't generate artifacts in conditions. So to avoid wrong behavior of the hearing instrument. So that is an active part of, very active part of the training of the systems. And maybe also important, the DNN, as I showed it, is very powerful and has lots of advantages. It has also some limitations because it's trained to extract the strongest speech signal. So if you have a very strong voice that you don't want to hear and a soft voice you want to hear, it can also fail, So it's powerful, but it's also not the holy grail yet. And we have to work on the system. Also, I think we have to learn to train it even more and better on other types of sounds like music. I actually never tried to listen through it to a pop song where you have a speech signal in a physical background of noise, whether it just suppresses the noise, I don't know. But it's a huge part of the training to provide good sound quality for all other sounds.
Yeah, thanks. And then we go on for the next one, which is I just go by order to be keeping it fair here. From Roman Stracke, do you also consider selective attention decoding based on neural or EEG data as a future use case for these DNNs in hearing devices?
Well, absolutely. This is a really cool functionality, and there is some really great work going on. It is definitely a future application. My understanding is that from a practical application, we still have a couple of challenges to solve around the electrode design, around the speed with which you can use this EEG or neurophysiological based measures. So maybe I would start with other measures like gaze detection or something like that before I would go for the EEG attention decoding, simply for a lot of practical reasons. But I definitely think it's something that we should keep exploring.
Okay, maybe two more. So the next one is from Liane Zeigers, where she is interested in how well these objective metrics that you presented relate to actual user performance or ratings later. For example, in cases that you mentioned, like where people perform better with overlapping speakers? Are those aspects specifically optimized while training the model?
No,
Or
they have not been optimized when training the model. The Q metrics measure that we used is described in a publication. And basically, what we did, we developed actually a neural network-based solution where we did listening examples with hundreds of listeners on many different sounds and had sound quality ratings. And then we trained a network to mimic these user judgments, and that's what we then used as a metric to judge the quality of the system. So it has been trained on multiple broad ranges of sounds, but for example, not specifically on this overlap paradigm that I showed.
Mhm. Great. And then a more technical question, I think, here from Alexander Linhardt. So he says, in our space, we struggle most with the computational complexities since we really rarely have access to custom NPUs or, I guess, neural processing units. So we came up with very low MIPS models for this task. What would be your top area of improvement for your current DNN model in this regard, I guess?
Well, I think in our system, I mean, it's always the network architecture and the structure, and also the specific network architecture for specific applications. I mean, one question is, do we always need these large full-blown DNNs if you want to extract speech in, for example, a soft background, or could you get away with smaller DNN models as well? That would be one of the topics I would focus on, but I don't know whether I understood the question. I'm also happy to take it offline.
Mhm. Great, thank you very much. I think there are actually quite a few more questions in the chat, which you can have a look at maybe later or so,
Yes.
or we take them up in the discussions. So sorry to those, but we want to move on now to Timo Gerkmann's talk. Yeah, if you could try to share your screen, Timo, and then
Yes.
I think we're all very keen to hear your side.
All right. Um, Almost there. Okay.
Great, then.
So
Yeah.
no hope now. Hopefully you can. Oh, I'm sharing my entire screen, right? That's not what I intended. Let me try again. This one would be better. All right. Okay.
Looks good. Nice.
Very good. Yeah, thank you very much for inviting me, and thanks, Stefan, also for this great start. Of course, it's very impressive to see what these guys at Sonova have achieved, right? To really get an NPU implemented on a hearing device that can have, let's call them big neural networks with maybe 5 million parameters or so. Now I will take a little bit of a different perspective, more the perspective of a university researcher, and my narrative will also be a little bit different. So I will first show what we will be able to do in the future, in future hearing aids, and then I go back to more stuff that is, or well, will be working maybe on your next device or something like that. Okay, but yes, so first of all, obviously, speech communication in everyday environments is still challenging for many hearing aid users. And that is despite the fact that, digital speech enhancement algorithms are implemented into these devices for many years or even decades. And of course, now this whole deep learning area jumps in, and the question is really, when would it really help, and when can we rather rely on classic signal processing models, similar to the question that Stefan just posed. And then also we already talked about the unique challenges for hearing devices. There are the algorithmic constraints. We have very small batteries, so to say. So we need to have a device with low power consumption, which restricts the size of the models. And we have latency constraints also, maybe 10 or 15 milliseconds. Then we have a lot of acoustic variability. There's spontaneous speech. There's the Lombard effect, that you speak differently in loud environments. Head shadow effects, which is different from a usual linear microphone array or so. You have the head in between. Head movements, which can be relatively fast, device occlusions. All of these are things we need to deal with. Then we also raised just the discussion about metrics, right? You train on some metrics. They are engineered somehow, but how do they really relate to perception? And then you need a robust solution, right? You want something that works always. In the best case, you can even enjoy your favorite pop song, as we have just discussed. Here, I will by no means address all of these things, but this is just to set the stage. Okay, so now we'll be talking more about speech enhancement, right? And in speech enhancement, well, there are two big cases, the single channel case where you just have a single microphone or the output of a beamformer, and the multi-channel case where you can, for instance, have a beamformer to exploit the spatial diversity of the scene. Now, if you have a single channel speech enhancement algorithm, then in stationary Gaussian noise with a traditional Wiener filter, you can get pretty far already, right? You can reduce the noise and make listening to the noisy speech less tiring, for instance. But of course, very often we have much more complex scenarios, and then you can really gain from using deep neural networks. So therefore, in single channel speech enhancement, for a long time in research, we use deep learning. And now I will jump a little bit into the future, at least for a perspective of hearing aids, because what we currently are discussing in the research community is that there are really two classes of deep learning methods. One is called generative approaches, which you know from, I don't know, ChatGPT or so. And then there are predictive approaches, which are more classic deep learning methods, if you want to call them that. In particular, I want to talk about diffusion models. We know diffusion models, for instance, as the backbone of image generation tools like DALL-E, for instance. And the question is, how can we use them for speech enhancement, and when would they be beneficial? All right. So in general, if you think about single channel speech enhancement, you have some microphone signal or noisy signal Y, which is maybe the addition of clean speech X plus some noise, and you want to retrieve the clean speech. Then a classic approach would be something like spectral subtraction or Wiener filtering, which work but have strong assumptions on the stationarity and perhaps even the Gaussianity of the noise signal. Therefore, now we have the DNNs coming in and two different classes, predictive and generative. And you can visualize the difference, the key difference between them by looking at the distribution of clean speech given the noisy observation. Then if you think about a classic predictive approach like a Wiener filter, for instance, what it aims to predict is the mean of the posterior distribution, right? So this could be the distribution of all Fourier coefficients, for instance, of clean speech. It can be a very complex multimodal distribution. And then if you're just estimating the mean of it, it is not always optimal. Generative approaches are different. They are more aiming at predicting the distribution of the data. And then you sample from this distribution, which is interesting because it's very different. And it also means that every time you call the neural network, you get a different result. And right, they will always be in the sample span of the distribution per definition, whereas if you predict the mean, it can also be outside the sample span as visualized here in this for example. More from a practical perspective for speech enhancement, if you have predictive approaches, then often they yield speech distortions, especially if the signal-to-noise ratio gets low. So this is a real visualization of clean speech, of reverberant speech, and a reverberation task. So here you see the predictive solution of the de-reverberation, where you see these horizontal lines that should not be there. So that's just an example of an artifact. Whereas with a generative approach, you get something that in the spectrogram plot looks much more rich. So, right, so these are spectrograms where the x-axis is time, the frequency, the y-axis is frequency, and the color code is the intensity per time frequency bin. Now, the predictive approaches, they may yield speech distortions, but they are relatively fast from a university perspective, in the sense that you only need to call one neural network once, whereas for diffusion models, you get this high quality, that's good, but you need to call a neural network multiple times, which just adds up to the complexity. All right, so what is really the idea of generative approaches or diffusion models in particular? You start off with an image. That's how it all began. For us, it would be STFT spectrograms, so short-time Fourier transform spectrograms, again with the frequency axis on the y-axis, the time axis on the x-axis. And then what you do is you gradually add noise to the speech signal and train a neural network that gradually removes the noise step by step. So you do a step-by-step denoising, which means you call a neural network many times, maybe 30 times or so, right? Which means you have 30 times as much complexity. And during inference, you take your noisy observation, you add noise on top of it, and then go back. And because of that, because you're adding random noise, you are always getting a different solution, which basically means you sample eventually from the posterior distribution as I just visualized. Then, if you look at the benefits, one of the benefits is that one can show that they generalize better to unseen data, which is, of course, important for hearing aids. There are different ways of dealing with this. Of course, you can try to get as much data as possible and train on it. Or you have something that is intrinsically less susceptible to variations in the data. This we show here. So here, this would be the SGMSE plus would be a diffusion model. This would be a violin plot of Moss predictions by means of Polka, where for the green histograms here, you have the same corpora for training and testing of the neural network. It's not the same data, obviously, but different subsets of the same corpora. Whereas in the orange histogram here, you see something that is trained on a different corpora than it's tested on. So it's really completely different speakers, different scenarios in which there are recorded different noise sources. And here we would like to see a nice symmetric violin, but you don't get this. It's a little bit worse in the mismatch case. But you see that for these two predictive approaches on the right, this problem is much more severe, right? So you get a little bit more robustness, which is nice. You can also play some examples. Works best with headphones, of course. For two tasks, denoising and de-reverberation. And this is now, so to say, the best you can get in a lab environment, so to say. Let me play this.
Some have accepted it as a miracle without physical explanation. To the Hebrews, it was a...
I think you can hear this, right? Is the audio working? Okay. Then the enhanced speech.
Some have accepted it as a miracle without physical explanation. To the Hebrews, it was a total...
So this was like a bar cafeteria background, and you can see or hear that the speech is, at super high quality. Also, de-reverberation is exciting because single-channel de-reverberation is an intrinsically difficult problem. The mathematicians would call it an ill-post problem, right? Let me play this one for you.
My head aches dreadfully now, not to say every word. I have only found...
And the de-reverberate signal.
My head aches dreadfully now, not to say every word. I have only found out. He is...
So this is super exciting, of course. It sounds like the original clean speech, right? It's hardly possible to differentiate between the two. I can play the clean, but let's do it.
My head aches dreadfully now, not to say every word.
So it's virtually the same. And it was a pretty high T60 time too, right? So this is quite exciting. But of course, the question is, how can this ever be helpful in the real world? Before I get there, let's also talk about some other disadvantages. Disadvantages first. Okay, so also low SNRs are challenging for the methods you are familiar with. In low SNRs, you get speech distortions. You can mend this by reducing the amount of noise reduction that you want to have. But if you don't do that, you get speech distortions. Here it's different because in low SNRs, you get phonetic confusions, which sounds a little bit funny. But let's play this. It's a super low SNR. So this would be the noisy, the enhanced, and the clean speech.
They were unbelievably expensive to administer. They might be limited to the local.
So it's hardly intelligible.
They were unbelievably expensive to administer. Can you remind me so very limited to the local?
So at the beginning it works quite well, but then it's basically nonsense. And before I play the clean, maybe I can show you something else. And that now I'm losing my mouse. Oh, there it is. That you can, if you use visual information, then you can guide the denoising process and make it intelligible again. So this is basically the same algorithm, but it's guided by means of the visual cues that you see here. And let's play this result.
They were unbelievably expensive to administer. They were time consuming. They were limited to the local.
So now we are looking really into the future. I'm basically saying if you have a hearing aid with a camera, then you can do magic with it. But yeah, so this is the thing. Hallucinations, phonetic confusions, you need to deal with that. But yeah, let's talk about the practical applicability. So it's really a challenge. I've been working on that a long time in the past few years to make this real-time capable. And now we're happy to show a real-time diffusion demo at the ICASP in May in Barcelona. This is a video of the demo. And basically what it's doing is it's doing this real-time diffusion with a reduced number of iterations such that it works on a laptop, right? So this is a laptop we'll bring to Barcelona and then play this video or play the demo. That is not the video. So we will use the real noise in the paper, the poster session there. Let's play this one.
We are excited to present our newest work on real-time, low-latency generative speech enhancement using flow matching. We follow a two-stage approach here, where a predictive model first removes reverberation and noise, and then a generative flow matching model enhances the speech and improves the speech naturalness. In this scenario, we are standing in a reverberant room with interfering speakers. When we enable only our predictive enhancement model, we can hear that it removes the reverberation and background noise well, but suffers from some unnatural artifacts. To fix this, we can now also enable the generative model, which removes and repairs artifacts and regenerates perceptually pleasing speech. The generative model uses multiple calls of the same network through activation caching and an optimized.
Right. Yes. So this was basically a jump to the future. It's exciting stuff. So we're getting better and better in terms of the size and the real-time capability. So as I said, it now works on a laptop, 24 milliseconds algorithmic latency. So this is quite nice. So that's that about diffusion models. So they can yield high-quality speech enhancement. They generalize better than predictive approaches. A little bit further into the future, there are challenges we need to deal with. Low SNRs, the complexity is still too high for hearing devices. Yeah, that's basically that. Then let me jump into another topic, multi-channel speech enhancement, where we are much closer to something that we can already implement on a hearing device. And the main reason for that is that because we have multiple microphones, we have spatial cues that we can use for a better speech enhancement performance. So the spatial cue is a very strong cue that we can exploit. So here the scenario is that we have multiple microphones, 3, it could be 4, maybe 2 per hearing aid or so. We have an enclosure, there might be reverberation that we want to get rid of. Then a classic approach, like you have on current hearing aids, would first do a spatial processing with a beamformer. This could be, for instance, a minimum variance distortion with response beamformer, but also something else. I mentioned that because I will mention it again in 1 or 2 slides later. Then typically you have a post filter, like a Wiener filter. It could also be a neural network, like a DNN-driven solution that is single channel, right? Okay. Now, if you look at the problem from a statistical perspective, the interesting thing is that if you, again, look at the posterior distribution, so here clean speech is denoted by S, and Y with the arrow would be a vector of microphone signals, then interestingly, whether you condition the clean speech estimator on the microphone vectors, or on all microphones, or at the output of the MVDR, is mathematically the same under some assumptions. And that's nice, right? Because if this holds, it basically means what you're doing is optimal and there's no need to train a neural network on the problem, right? Because it's intrinsically a linear problem. Why would you train a nonlinear neural network to solve it? It's an overkill, right? And the assumptions under when it holds is that the noise is Gaussian. That's basically all you need. You need the noise in the Y vector to follow a multivariate Gaussian distribution. So that is often a good assumption, for instance, in diffuse noise or diffuse stationary noise, or if you have reverberation, for instance, in the tail of the reverberation. But very often it's also not, right? For instance, if you have a multi-speaker scenario or so, then clearly the noise sources are not Gaussian. And then, and I spare the math with you, the solution gets very complicated, actually. You can solve it on paper, but you have nonlinear functions in there. It's a joint filter that you cannot separate between spatial and spectral processing anymore. And then basically the question is it really worth getting at it? So here you have this known approach, which is computational lightweight, easy to steer and to adapt. It's very interpretable. It's even MMSE optimal, minimum mean squared error optimal. If you have Gaussian noise, it's not optimal if it's not Gaussian noise. Then for the other solution, you instead have a joint filter that jointly processes spatial and spectral information and also in a nonlinear way. So it's very complicated. And it's almost impossible to solve this with the classic signal processing solutions. But neural networks are general nonlinear function approximators, so you can estimate the estimator in a data-driven way by means of a neural network. To see if that's worth it, we did several experiments. I'm showing one of them. This would be Polka mean opinion score predictions, where in blue you have a beamformer plus a post filter, so an MVDR beamformer and a post filter, where on the x-axis we control the kurtosis. So kurtosis is a measure for Gaussianity. So if the kurtosis factor is 1, you have a Gaussian, and if the kurtosis factor is 8, it's very non-Gaussian, right? And then you see that for the optimal solution, so this is now the Oracle solution that you can put on paper. For a very high kurtosis, you gain up to 1 full point on the Mohs scale, which is not which is quite a lot. It's not negligible, right? So that's great. But then, yeah, how to realize this in practice? And as I said here, you can use pretty lightweight neural networks. So the first proposal we made here is a neural network with only 2 layers. It has 2 LSTM layers. So these are recurrent neural networks, where one of them runs over frequency. That's what we call the FLSTM and in the short-term Fourier transform domain. And then the other one runs across time. So then you can train it with training examples, which is great. You can also make it steerable, right? So you can tell the algorithm during training what target direction to focus on, which is nice. We do that with a little trick where we, so such a recurrent neural network always has a memory cell, similar to an autoregressive model or so. And this one we initialize with the desired target direction. That's basically the trick. And that is then a demonstration where we implement this on a hearing device, right? So these would be satellite hearing aids that we put on an artificial head, but the artificial head is really only there to act as a shadow and to hold them the hearing aids. And then we basically have 3 sources. Alina here stands at 100
when the sunlight strikes
35
raindrops
degrees.
in the air.
So we first focus on Alina, and then later we focus on the left ear, so which would be Jakob then. So let me play this to you.
With its path high above, and needs to end apparently beyond the horizon.
Let's go
There
back.
is
Get the
according to
noisy
legend.
also. Okay.
When the sunlight
This
strikes
thing
raindrops
is
in
Sorry, one more thing to say. This is also binaural, right? So if you have hearing, headphones, you can hear that it's a binaural recording.
when the sunlight
This
strikes
thing
raindrops in
is
the air, they act as a prism and
with its path high above, and needs to end apparently beyond the horizon. There is, according to legend, a boiling pot of gold at one end. People look, but no one ever finds it. When a man looks for prism and form a rainbow. His friends say he's looking.
Now we're looking to the left ear.
These take the shape of a long round arch with its path high above and its 2 ends apparently beyond the horizon. There is, according to a legend, a boiling pot of gold at one end. When a man looks for something beyond his reach, his friends say he's looking for the.
All right. Yes. So that's basically what I wanted to talk about. So we see that AI and deep learning is a powerful tool to ease speech understanding and noise. We talked about 2 different things, the generative models for single channel speech enhancement, where we showed that diffusion models are really exciting because they can create enhanced speech at quality that you have not heard before. At least I was super excited when I first heard it, with the problem that we have a computational complexity that is not quite within reach for hearing devices. And then we talked about DNNs for multi-channel speech enhancement, which are much smaller neural networks that you can already implement today on hearing devices. They still yield very powerful results and are especially powerful if you have more speakers than microphones, which is exciting. And that's basically it from my side. So thank you very much. And let's see if you have questions.
Great. Thank you very much, Timo, for this great and super exciting talk. I think you're right. The future is very interesting. There's all the virtual applause coming in for you. You can see that, not hear it, but yeah. I also really liked your demos and sound examples. That's much appreciated. I think it gives people a really good idea how this sounds and what to expect. Really great.
Thanks.
Really cool.
Yes.
Before we give a bit of time. Oh yeah, there's the first question coming in. I would wanted to ask one myself quickly. Use this
Yes,
chance
please.
that I have. So it's really exciting, I think, and how you described this like new type of generative models here now. Um, could you say quickly, so because they're generative, would they really generate from scratch the voice, or would they, as you shown, add noise and filter out the underlying signal again? So how can you ensure if it would generate from scratch? That it keeps the sort of speaker characteristics, cues, and speaking style and voice, etc.
Yes, so there are different classes of or different ways to deal with these diffusion generative models for speech enhancement. What we proposed is an approach that is supervised. So you train on pairs of noisy and clean speech. It's a little bit mathematical, but it's defined by a stochastic differential equation. And then the trick is to get the noisy speech into this equation. Other than that, you would just train on clean speech and somehow need to guide it. That's similar to what DALL-E does, right? DALL-E means you have a text prompt and say, I want to have a picture of an auditory seminar or so, and then it will generate some picture, and then it's a little bit more difficult to guide. So here we are really starting with the noisy observation. So therefore, the output will always also sound like the speaker you have, right? But of course, again, the lower the SNR gets, so the more of the speaker characteristics are masked, the more that can basically offset from the original sound. But this really, to our, from what we heard, not a big problem. Typically, it's much more of a problem that if you go to negative SNRs, that sometimes the phoneme gets confused. That happens much earlier than that the speaker characteristic would change, right? So that works actually quite well.
Okay, very interesting.
Yeah.
Yeah, so then we have a question from Marta Campi here, maybe also similar in a conceptual sense here. So regarding the generative single channel part, if I run you a diffusion model twice on the same noisy input, I get two different outputs, as you
Yes.
described. For a hearing aid user, is that a feature or a bug?
Yeah, that's a generally very interesting question. So these generative approaches are relatively new, and there are many things we need to discuss. For instance, along with this question comes the question, how do you evaluate these algorithms? Because typically what we do, if you think about instrumental metrics, I'm not talking about listening experiments, right? I mean, this is pretty clear. You just listen to it and rate how it sounds. But if you use instrumentive metrics, you always compare it to one specific realization of clean speech, right? So you really look at how close is the thing that you sampled to one certain utterance, so to say, sample by sample in a sense. So so here it would be different because every time you call it, you would also get a different number. Now, is that a bug or a feature? My take is that it's more important that you get good and high quality rather than getting the exact replication of some underlying clean speech signal. So I wouldn't say it's a feature for a hearing aid user, but I also don't think it's a bug. That would be my answer.
Mhm. And then we have a question here from Jan Willem, who talks about misophonia. Maybe you've heard about that, where people do not like or are quite sensitive to certain types of sounds like chewing or coughing or other things. So he asked, or could you train DNNs to remove these unwanted sounds?
Yes, you can. You can. What is exciting, again from research perspective, is that if you don't control it, generative algorithms will also produce such sounds, like breathing artifacts, for instance, right? It would sound like you're inhaling while you're not, right? So in other words, these generative approaches are much more expressive, and they can generate also such artifacts, right? That you hear somebody inhaling while he's not inhaling. On a level, I mean, like on a level that you would have in the training data, right? So if you have training data without such sounds, then it would also not be replicated in the enhanced speech. So a lot of these things, to answer your question, is related to the training data and your training targets, right? Whether or not you want to have such sound in your algorithm or not. I mean, you could also argue that it makes the speech sound more natural, because in natural speech there would be breathing and chewing sounds, right? But again, I would agree that if you have a hearing aid on every day, maybe you want to reduce these sounds. Don't want to treat them as noise rather, right?
Mm-hmm. And then from Joanna Luberacka, could the generative approach cancel just the noise but preserve the original reverberation, for example?
It's a good question. You can train it to preserve the reverberation and reduce the noise, yes, but we have not tried this. So I'm not sure how good I mean, of course you can do it. The question is, of course, how good does it work? And that I have not tried, so I cannot really give you an answer. But my expectation would be that it would work quite well. But the proof is in the pudding. We have to try.
Yeah, I guess that makes sense to keep sort of the acoustic environment sounding plausible to the listener, say, if you're in a reverberant environment, right? So, yeah.
True. It can have, add to spatial awareness and these things, indeed.
And then from Alexander Linhart, how consistent is the output of the generative model output between the left and the right ear? If you had a binaural system, sort of.
That's also a good question, very good question. So far, in generative approaches, we have only worked on single channel approaches. So the binaural examples that I played for you were not generative, right? Those were predictive approaches, lightweight approaches that can run on hearing aids already today. With respect to multi-channel diffusion-based models, there are just coming up approaches here and there, but it's very few still, right? So it's a relatively new and unexplored topic. So in other words, I don't really know. It's a good question, but there's still work to do in that field for sure. Yeah.
Yeah, it's very interesting. And then maybe the final question for you now in this part of the question and answering is from Rachel Ellinger. So besides the visual data augmentation that you showed, yeah, are there any other complementary inputs or signals to sound processing that you see being useful in the training of future DNNs?
Right. I mean, the most obvious one we just briefly mentioned would be spatial cues, right? That would be strong guidance to help the algorithm for sure. But then anything that helps can be used. It could be vision. It could also be EEG signals or so, or some gaze tracking or what have you. So the thing is, with these new deep learning era, you can very easily augment the data with almost anything, right? Which is cool. Sometimes it's a bit scary because it's so easy, but yeah, I mean all of these things that we have been discussing in the community, for instance, to track the attention or of the listener, right? What he wants to attend to. for instance, by means of EEG signals or so, you could use in these algorithms, right? Yeah.
Yeah, great. So I think there are still questions coming